We'll see how this video goes. I just got a pop-up that says my computer is filing or installing virus updates, as you can see from the pop-up there. And as I said before, this computer is not exactly state-of-the-art, so we'll do what we can. So reactivity is determined by ionization energy and electron affinity. It depends on which type of element you're looking at, whether it's a metal or a non-metal. When you're looking at metals, it's ionization energy that is the most important. As a general rule, when you're dealing with a metal, the lower the ionization energy, the more reactive that metal will be. For reasons we're going to be learning about in great detail when we get to our next unit on chemical bonding. Basically, in a nutshell, to kind of foreshadow where we're going, metals tend to lose electrons when they react. And since ionization energy is directly related to that, it's the amount of energy needed to remove an electron, it's going to be the trend that governs how reactive they are. The lowest ionization energy is in the bottom left corner of the periodic table. It's cesium, Cs. Francium is a little bit higher because when you get down into francium, you start dealing with those weird f orbitals. Those f orbitals really mess things up in terms of trends. But basically that bottom left-hand corner is where you find the largest atoms. So in that bottom left-hand corner, you're going to find the lowest ionization energy, which means you're going to find the most reactive metals. Again, because we find the lowest ionization energy in the bottom left corner of the periodic table, we can say the most reactive metals are found there as well. The closer to that corner you get, the more reactive the metal gets. If you recall back to when we were talking about families, we're talking about how vigorously these different families of metals react with water. We said group 1, the alkali metals, react vigorously with water. They'll catch fire, they'll explode. Group 2, the alkaline earth metals, will react with water, but only under certain conditions. When you get into the transition metals, they really don't react much with water. You see that reactivity decrease as you move over to the right. Your most reactive group is group 1, the one that's furthest to the left. Within that group, the reactivity will increase as you go down. So again, sodium will sputter, throw off some sparks. If there's enough of it, it'll catch fire. If you put cesium in water, it downright explodes because you're at the bottom of that group. You're dealing with a much lower ionization energy, and it's much more reactive. For non-metal, the trend is driven by electron affinity, how much energy they lose, how much more stable they become when they gain electrons. Higher electron affinity means more reactivity. Now you'll notice in the boxes for the noble gases there are X's. It's because they don't react with anything in nature. So we're looking at group 17 on the periodic table. Hydrogen is over there for, I really don't know what reason, so just ignore that H. So fluorine, chlorine, bromine, iodine, and astatine. You'll see the electron affinity is very high at the top of that group. And again, the higher the electron affinity, the more reactive that non-metal is. So again, ignoring noble gases because they're completely stable and they don't react with anything. The highest electron affinities are found in the top right corner of the table. As a general rule, the closer you get to that corner, the more reactive the non-metal will be. So in terms of arrows, if you're looking at your metals, you're going to the left and down. That's where your reactivity increases. You find your highest reactivity for metals in the lower left-hand corner of the periodic table, where the largest atoms are, where the lowest ionization energy is. For your nonmetals, you're going to the right and up, over towards fluorine, because that's where your smallest atoms are. That's where your highest electron affinities are. That's where you'll find your most reactive nonmetals. That wraps it up. We can move on to something new next.